Welcome students. In today's class we are going to discuss about various optimizations and their impact in high level synthesis results with some examples case studies. So, start with we will talk about this code optimizations or generally optimizations. They have a huge impact in the final outcome, right. So, in terms of performance, area, power and timing. So, I have taken two such examples. So, for example, it says that 1% performance improvement saves Google $1 million in data center. So, just having a 1% performance using some kind of optimizations can save $1 million, right. This is a good study. On the other hand, once you do this code optimizations, you are changing the behavior of the input specification, right. So, if you are not doing it carefully, you may end up having incorrect functionality, right. So, you have to do these things very carefully in the other hand also, right. So, we have an example here where I am saying that some European Space Agency spacecraft was the rocket failed to achieve orbit because of some problem in the date code and specifically using integer overflow, right. So, I am just taken two arbitrary example from internet just to emphasize this to impact, right. So, on the other hand, this code optimization is very important in terms of performance improvement, and this performance improvement can give you a huge benefit, monetary benefit. On the other hand, it has to be done very carefully. Okay. So, in context of high level synthesis that I have already discussed, that this high level synthesis specifically for behavior where there is no array and loop, high level synthesis can synthesize the things into hardware efficiently. But in presence of loop and this arrays, we found that this high level synthesis may not able to give you the best hardware always, right. So, you need to understand how to apply the loop related optimizations of the high level synthesis tool as well as the optimizations related to the array in the high level synthesis tool efficiently for efficient generation of hardware. Okay. On the other hand, many a time this synthesis tool may not able to apply or may apply the optimizations, but since it is an automated tool, it may not understand everything on the specification. So, the user may need some time a manual modification of the behavior as well. Okay. So, and also we have seen that this task level pipelining or data flow, which is basically to achieve the maximum performance in the hardware by doing the parallelization of the behavior in the hardware, that is also very important in the making a efficient hardware. Okay. So, what I am going to do in this particular class, I am going to primarily take the example of matrix multiplication, and I am going to see how this loop unrolling, pipelining, array partitioning and then this task level pipelining actually helps to achieve a better hardware. To start with, let us first take the matrix multiplication example, right. So, I think it is all everybody knew that, but just for refreshing your memory, I am just explaining what is matrix multiplication. So, we have given two matrix A and say B, or you can say this is mat 1, matrix 1, right, and matrix 2. Two matrix is given, right, and the size of the matrix, the 1 or A is basically say m into n, right, and this is n into say some p. If you do this matrix multiplication, that means A has m number of rows, n number of column, and this B has n number of rows and p number of columns. You will get a resultant matrix if you do a multiplication of these two matrix, which will be of size m into p. Okay. So, in this discussion, for making the process simple, I will just assume this all m, n and p all are same size. So, I am going to consider arrays n into n, right, and the resultant matrix will be also n into n. This is for simplicity, but the whole discussion actually valid for m and p as well. Okay. So, what it does, matrix multiplication, just to recap, is basically you to calculate one element of the resultant matrix C. So, this is C, this is B and this is A. What we do? We take a row of this array A, we will take the column of the array B and we multiply element wise, right. So, that means to to obtain this element, right. So, to obtain A11, sorry, say that AB11, I am going to multiply A11 with B11, then I am going to multiply A21 with A12 with B21 plus A13 into B31 and A14 into B41, right. So, to obtain a single element of the resultant matrix, I need to take a row of the A array, one column, and if I do the element wise addition, multiplication and then the addition, that will be my resultant matrix, right. So, this is how I can calculate. So, for example, to obtain this element, what I have to do? I have to take this row and this column, right, that will give me this element, right, and so on. So, this is what is matrix multiplication. So, you can understand to for a given n cross n and n cross s matrix, you need kind of order of n cube number of multiplications, right, because for a single element I need n multiplication, right. So, for this is 4 cross 4 is 1, 2, 3, 4, right. So, 4 multiplication, and so there are n square element here or 16 elements. So, 16 into 4 64. So, it is kind of order of n cube multiplication and also order of n cube addition operations, right. So, although this code which is actually calculating this matrix multiplication, it looks as very simple 4 5 lines code, but it actually is very computation intensive, because for a n cross s matrix multiplication, it is kind of order of n cube multiplication operations and n cube order of addition operations. Okay. So, let us see this code, what is happening. So, what is happening, this is the output locations, right, I and j, right. So, for each output location I and j of the resultant matrix I and j, I am doing n multiplications, and this k is basically is the n multiplications happening in the this internal for loop, right. So, what is happening here is basically I k into k j, right. So, that means I am taking the row here, I am adding the k. So, I 1 1 1 2 1 3 1 4, and this is I am adding the column. So, it is basically taking the column. So, keeping j fixed. So, basically it is 1 1 2 1 3 1 and so on, right. So, this particular loop actually doing this multiplication and addition for a given location for each I j location, right. This is what is the multiplication code, and as I mentioned, this particular code also look very simple, only 5 6 line. It is kind of very computation intensive. So, you need to take some proper care for making a efficient hardware from this particular loop, right. So, one of the important optimization is loop unroll. So, you can unroll this loop. So, there are 3 loops are here. You can unroll this innermost loop. So, if you try to unroll the innermost loop, what is going to happen? So, you can see there are kind of n cube number of operations, and if you unroll the innermost loop, that means you are actually removing this loop, right. So, that means for each output location, whatever the n of multiplication is needed, that is going to be flattened now, right. So, that means if you just unroll this innermost loop, you need order of n square kind of time step. If I assume that here I need kind of order of n cube time step, because in every iteration one multiplication followed by addition is happening, but if here this, since the innermost loop is unrolled, you need kind of order of n square of time step, right. So, in similarly you can actually use this unroll in the middle loop, right. So, instead of here you are putting here. So, that means you are actually unrolling both the loops effectively. So, if you have a innermost loop and if you put the pragma in the top loop, that means both the loop will be unrolled. So, effectively you need kind of order of n timestamp, because both the loop will be unrolled now, it will be both the unrolled, and that means this is only for the I loop, all the things will be unrolled, right. So, and you need kind of order of n time. I am assuming that all this operation is going to be executing constant number of timestamp, right. Similarly, you can, if you put this unroll in a topmost loop, then every loop will be unrolled, and is all, there is no loop at all, right. So, then you have kind of constant time to execute this. But obviously, this performance improvement comes with cost, right. So, here probably if you need a single multiplier, here you need order of n multiplier, here you need, if you put this in here, it is order of n square multiplier, and if you put this in the topmost level, it need order of n cube multiplier, right. So, in the sense that you need to make a balance between these two, right. You can order of n cube multiplier, if you just think about 10, n equal to 10, it is basically 1000 multiplier, it is not available in many target device, right. So, you need to make a proper balance of that. So, what I am going to do is I am going to take this particular example and try to put this unroll in the innermost loop and try to see how it is going to impact the performance. Okay. So, now you can understand that so for one element there are n multiplications, right. So, there are n square elements. So, the order of n cube multiplications are happening here. So, it is very computational intensive program, although looks like a 3-line 4-line code, but it is very very complex computation intensive program. And also there is a adder, memory read, there are 2 memory read, so 3 memory reads, you are reading from the resultant matrix and you are writing back, right. So, obviously if you run this program, it will take, the latency will be very high. Okay. So, the idea here is that if I try to apply unroll, loop unrolling, how it will improves, right. Obviously, you can understand that unroll means basically you flatten the loop, right. So, there is no loop at all. So, the good idea to unroll here is that you basically unroll the last loop, right. So, that is what I did here. So, basic idea is that whatever the multiplication I just talked about, I do not want to write the loop, but I will just write this direct equations, right. So, if I just replace this unroll, effectively it means it is basically for each element I am just writing these equations where this I and this 1 is basically I j, right. So, I j k. So, if I do that, obviously what I can, that I can now run these things parallel, right, because these all operations are there. So, I can schedule them differently, I can run them parallelly. So, let us see how, if I just do this, how it will impact the performance. So, you take, so I just take a 3 cross 3 matrix and try to run it for some target architecture, and what I see, if I just run without this unrolled pragma, I get basically 215 cycle clock cycle is needed, the latency is 215 cycle. Okay. And if I just write this, apply this pragma, it is basically taking 89 cycle. So, it is kind of 1/3, right, because this is a 3 cross 3 matrix. So, it may not be exactly multiplication of that, because there are some clocks needed to synchronize the pre and post operations and so on, right. On the resource side, let us see, is it something 3 times more, let us see. So, earlier it was since it is a small array, it is not using any BRAM, it was using 6 DSP, which is basically the multiplication operations happening there, 320 registers, because this array mapped to registers, and these are the combination with 685. What is the change now? It changed to 6 to 12. So, it is get double, right. So, you might say that now I unroll, that means all this operation is happening parallel, why it is not 3 times, because there are 3 multiplication is going to happen, right. The answer is the scheduler may not schedule everything in one cycle, right. Based on the that combinational delay, it might decide that I am going to execute in say 2 cycle or whatever it is, right. So, it is not that if you just unroll you will get that multiplier, because multiplier will be 3 times, because I take a 3 times 3 into this 3 cross 3 multiplication, right. It depends on the how now a high level synthesis tool schedule. Obviously, it will increase, I can see the increase in the register also, and also in combination unit, obviously because of this handling this interconnections and all more interconnections. Okay. So, I can clearly see that from if I just apply unroll there, my latency improves 3 times, my number of time clock needed is reduced by 3 times, and my area overhead is not 3 times. So, if something is useful, right, because performance is greatly improved. So, one might ask me that if I do not unroll, why it is taking 6 multiplier, right. The answer is, so if I am here taken integer, right. So, my elements are integers, right. So, it is 32 cross 32, and in the DSP board Usually the multiplexers are not this multiplier are not 30 cross 32 cross 32. It is usually say 16 cross 16 or some specific things. So, and then that means what? So, achieve this you need to split it into smaller multiplier and you have to combine them, and that combinations it can be different, right. So, there are some many algorithm where there are many way you can actually break a bigger multiplier into smaller multiplier and combine the result to get the better results. So, that is why even if during rolled implementation I am although there is only single multiplication in each iteration, but still it is 6. So, this might vary for the target architecture, because if I take a different FPGA board, the DSP configuration may be different, right, and based on the DSP configuration the number of multiplier will be decided. So, here I probably taken a very smaller board, so that is why it shows more than 6 multipliers, right, but I hope you understand the overall idea here. So, in unrolling you can understand that if you just completely unroll, the number of operations grows very high, right. So, the usually it is getting controlled by a unroll factor, right. So, you can unroll the loop completely when you make it k equal to 1, unroll factor equal to 1, or you can unroll by 2, or you can unroll by 4 and so on, right. So, this is unroll factor you can use, and you can understand that it is basically partially unrolled, right. Here I just put some results, I just take a now 8 cross 8 matrix, and for rolled implementation this is the resource utilization and this is the number of clock cycle, right. You can see here there are 9 DSP, the multipliers, and these are the other units. When I completely unroll, my multiplier is not 8 times, right, it is only 4 times, because it is 8 quadratic matrix multiplication. If I unroll, there will be 8 multiplications within the inner loop, right, but that is not 8 times. So, again the reason is that I have explained. So, again if I just do a unroll factor this, you can see here it is kind of 2.5 times, right, and you can see here the reduction in the clock time is kind of almost 4.5x, right. So, you can understand that how much improvement you can get in the number of clocks and the number of resource, and based on the available resource and the available budget, you can decide which will be your best factor you should choose, whether you are going to completely unroll or partially unroll, right. So, that is something this unrolling, and it is basically useful for bigger very complex loops, where that you cannot, if you just completely unroll, probably you just cannot fit the everything into the FPGA board, because it just might be resource might overflow, right. So, this unroll factor can be a key things to manage this blow up in the area. Okay. So, the next one is the instruction level pipelining or loop pipelining. So, you know that this high level synthesis tool support pipeline. So, if I just apply this pipeline in the innermost loop, what will happen? Now, this multiple iterations of the loops will run in parallel, right. So, I am not going to detail how the pipeline works, but that is already explained, but it is basically you can understand that obviously the number of clock cycle is going to reduce, because now this different iterations of the loop are actually overlapped, right. So, let us see in this particular example, again I just take a 3 cross 3 matrix and I just try to run, and this is the result I have already explained. There are for basic baseline case where we do not apply any optimizations, we take 215 cycles and this is the resource, and now I just apply this pipeline, I can see 167 number of clock cycle. So, it is basically because it is a 3 cross 3, the number, the advantage or the benefits are getting less, because the number of time you run the loop, your benefit will be more, right. So, since the loop is the innermost loop is only 3 times, the benefits is not that significant, but if you just run the same thing for say 10 cross 10 multiplier, this will be a significant improvement in the number of clock cycle. But most importantly, here you see the number of resource does not increase much, right. The number of multiplier remain the same, flip flop reduces, and there is a small increment in the number of LUTs. So, this suggests that the pipelining is something one of the most powerful optimization technique in high level synthesis to get a good performance of the loops, because it does not increase the resource by much, but if the number of iterations of the loop is more, the benefits of the number of cycle or the latency will be greatly reduced by pipelining. Okay. So, let us move on. The next most important optimizations is the array partitioning, and it is kind of inevitable, you have to use it, and because of that the problem that of the block RAM. The block RAM has 1 or 2 ports, So, you can have only 1 or 2 access to a memory, right. And when you have array, if you have more than 1 access, more than 2 accesses, it's create a bottleneck in the loop pipelining also, right, because if you just put it in, there is a array access, more access in the loop, you try to pipeline, you may not achieve this pipeline initiation interval of 1 because of this access limitations. Okay. So, array partitioning is something important, and this high level synthesis tool does support that, right. So, for this I just first taken a matrix addition example first, and then I will move on to the matrix multiplication and how this array partition will help there. Okay. Let us take a 16 cross 6 bigger multiplications and try to add it, right. You can understand here this addition is very simple, that if you have 2 matrix and if you try to add it, basically it is element wise add, right. You just add these 2 element and store here, you will add this 2 element, you store here, right. This is basically element wise addition, right, that is what is happening here, it is a 2 nested loop. And if I try to pipeline it, you can see here when I am not able to get the initiation interval 1 because is become 8 here. If I just run it in high level synthesis, you can get it. It will say that unable to schedule the load operations because there are so many memory read, the matrix load 1 and so on. So, because of that target pipe initiation interval is 1, but I am able to achieve initiation interval of 8 and my pipeline depth is 9. Okay. How it is coming here? So, you have to go into deep understand, because these things will be split into 3 address operations and it can be split in more operations, that is why we have a depth of 9 there. So, you can actually run and see the schedule and you can understand the much better there. But the problem is you can understand that because of this so many memory read, we are actually it is creating a problem, right. So, what we can do is basically we just unroll it. So, basically we can split the array, right. So, what I did it here is basically I just split the array into 2 dimensions. So, basically I just split the array by 2 kind of, right. And now I can run this operations in parallel, and basically you can see here that my now I equal to 4, right. So, basically by just partitioning the array, I am actually making enabling this loop pipelining because I am actually applying pipeline in the outer this outer loop, not here. So, if we apply here, what will happen? It will basically unroll this loop, that is why this is happening. So, just to explain again. So, you can see here I am not applying this unroll a pipeline at the innermost loop, I am applying in the outermost loop, right. As a result, what is happened? This is going to unroll, right. And if you unroll, you can understand that there will be so many memory read, and because of that you are not getting this incident 4. But because this operations are element wise multiplication, is a symmetric access. So, what I can do, I can just split the array by like this, right. So, then what I can do, I can whenever you try to run this, so if even if you unroll this this 1 to 0 to n. So, basically what will happen? That you just add this element, right. So, this is basically I j. So, and if it is 0 to n, that means it will these columns, right. So, it will just do these columns 0 to n columns, and what is going to happen? So, this part of the things array access will be from one array, and this part of the array will be accessed from the another memory. As a result, you can actually do this access parallel, and that is what exactly happening here, and that is why my pipe initiation interval will become from 8 to 4, because I just split in 4, and if you split it more, probably you will get better this initiation interval, right. So, we can understand that array partitioning is something is important just to reduce the memory accesses. Let us now discuss the results here. So, if I do not partition the array and if I synthesize into FPGA with some target device, this is the latency I am getting, right. So, it is a 130 cycle, right. So, that is what I am going to get, and if you look into the resource, since it is a matrix addition operation, there is no DSP, no multiplication. The array, it is a small array, so map into flip flops, no block RAM, but it is all mapped to flip flops, and you need some conventionally you need to execute the other operations, right. So, now you think about this after array partitioning, manual array partitioning, since I partition the things into 2 arrays, so my latency is almost half, right. So, latency improves, right, double, right. So, your performance get double basically, right. And if you look into the resource, again there is no block RAM, no DSP, but I can see the flip flop reduced to almost half, and LUT increased little bit because of managing this partition thing. But I think one of the reason for this reduction in the flip flop probably is the reuse of the same flip flop to store the different partition of the array. Okay. So, it clearly says that this array partitioning help improving the performance of the matrix addition without much increase of the resource. So, now for array partitioning is something HLS tool does, right. You can just apply this array partitioning this pragmas and you can do that, but sometime you the tool am not able to decide, right, or you are not able to for tool it may be difficult to basically partition and if the access is not so symmetric, right, and this the classic example is the matrix multiplication, right. So, let us try to understand that how we can partition array to make this so that matrix multiplication get benefited, right. So, again you can notice here that I am applying this HLS pragma at the second loop, not the innermost loop. So, that means this loop will be unrolled. So, let us decide that I partition this array A by half in the row wise, right. So, I just make it it was n cross n, I just do this n by 2 into n, and this is also n by 2 into n, and the column matrix I divide by half by column wise. So, it is basically this array is basically n into n by 2 and this is also n into n by 2, and I decided to split the resultant array into 4 matrices, everything was n by 2 into n by 2, right. So, this is one part, this is one part, this is one part, and this is one part, right. So, this is how I split into 4. So, now let us see how this will help, right. So, let us try to understand this. Important point here is that say if I want to calculate these elements, okay, these 4 elements. So, to calculate this what I need? I need this say so basically it depends on how to consider. So, you can actually assume that this is B and this is A. So, if I multiply this into this column I will get this, right. So, similarly if I multiply this row into this column I will get this. If I multiply this row into this column I will get this. If I multiply this row into this column I will get this. So, what I can understand that to calculate this 4 element accessing this array and this array is sufficient. I do not need to access this part and this part, right. Similarly, for other components. So, if I try to access this, if I just multiply this part with this part, I can show that I will compute this part of the memory, and I decided that I have 4 different part, right. So, what I can understand here is that similarly if I just multiply this part with this part I will get this part of the resultant array, and similarly if I just multiply this with this part I am going to get this part of the resultant array, right. You can verify it. So, the here we can understand that now I can actually partition, and this partition actually helps, right, because if I partition this way I can actually kind of parallelize this part, right, because now I can run this 4 component, this component calculation of this component, this component, this component and this component is kind of independent, right. So, and then I can actually kind of put this into 2 different memory, this part and this part into 2 different memory, and this 4 part into 4 different memories. Then this I can actually kind of separate out the dependencies, and I can actually run these things in parallel, right. So, for example, I can just take this and this, and I can calculate this at the same time. I can just take this part, the other part, this part and this part, and I can do multiplications, and I am going to write this part of the array, right. So, that means I can actually these 2 are kind of independent and this access is not interdependent, right. So, this is what I can do, and the tool may not understand this and may not able to partition this. So, here I just do it manually, right. So, what I did is basically I just split my resultant array into 4 n by 2 in arrays, that A array into n into n by 2, and the other part is n by 2 into 2 arrays. This I split into column wise, this I split into row wise, and then inside this loop I just do these 4 operations in parallel, right. So, I can do these operations in parallel, that is the biggest advantage, right. So, what I can do is I can multiply this into this, I will get at the same time I can multiply this with this, I will get this element. At the same time I can multiply this with this and I will get this same element, and I can multiply this with this and I can get this same element, right. So, this is how I will do that, because now I can just read once. So, if I just read this element using that I can calculate this one element for each memories. So, this is what is the advantage you will get, and this is something what I did here, right. So, this is how I can actually parallelize this operations in different memory access, and sometime doing by tool is difficult. When nowadays there are tools which can actually do that, but usually we have to do this kind of partition manually to improve the performance, and let us see how it impacted, right. So, you see initially if you do not apply any optimization, it takes 2052 clock cycle, now it is taking 516, because I just kind of 4 time faster, because I split my resultant array into 4 and I am actually calculating 4 different element of the resultant matrix at the same time. So, it is kind of 4 time improvements. Okay. And the area wise also, since I am actually performing this multiplication. So, the number of multiplication is kind of 4 time more, and the resource is also kind of has a significant improvement, and it is expected, because I am now doing this things in parallel. So, you have to need more resources, but I can see there is a huge improvement in the time, right, the number of time required to execute that. So, this is what I just this how this matrix multiplication can be, the array can be splitted and basically it can improves the performance of the generated hardware. Okay. So far what I discussed is about either apply loop unroll or you apply a pipeline or you partition array, but I did not talk about the parallelize these operations, right. So, how do you parallelize these calculations, that is very important, and that is where is basically the data flow optimization. So, where I mean I am calculating the whole matrix multiplication, can I parallelize certain operations, right. So, and that actually give you huge benefit, right. So, let us try to understand that. So, what I did here is I have this bigger array, right. I just split it into smaller array, right, of size 4 by 4. Okay. So, what is happening? So, try to understand that this conceptually. So, I am going to explain this in conceptually, that I just do this, right. So, this is basically loop tiling, you can understand that, right. So, what I did here is basically earlier it is n cross n. So, this is 0 to n, you can understand this is all n, and now it is basically m by 4. So, basically whatever the size, I just make it 4, and then internally I just run another loops, basically this is 0 to 4, 0 to 4, 0 to 4, right. What does it mean? You have this bigger array, and this is applicable to all 3 arrays. I am just taking about one example, and I am actually try to split the whole thing into small matrix, right. That is what is happening, and that is what is exactly this, right. So, this is basically I split the whole thing. So, this calculation is for this, and this is happening for each such P, right. So, that is what this loop tiling means, and I can actually split this way, and the advantage of doing this has huge, right. So, what is going to happen, you have to understand that to calculate a element of the resultant matrix, I will multiply 1. So, just to give the example. So, to calculate one element of the resultant matrix, what I usually do is basically I multiply one column into one row to get this element, right. But in the basic idea is that intermediately I can just store some of them, right. So, basically what I can do, I can just do this 2 element multiplication, this 2, and result I store here. I will come back after some time, and then I will multiply this 2 with corresponding this 2, and then that add I will just put it here again, right. So, on top of that is a result plus plus, right. This is the plus, right, and then I will come back, and then I will take the next 2 element, I multiply the next 2 element, and that add is multiplication result, again I just sum up with this, right. And that is what I try to mean here, that to calculate the result element, one element, I can just take this part and and let us assume that the column matrix is that. So, I will just take that. So, I will multiply these two, I will store here. I will take this block, I will take this block, I will multiply the first row and this first column, and then I will add that on top of that, right. So, what I try to mean here is that if you just do this, there is no nobody tell us that you have to multiply all this column, all this element of this column y, I mean one column and one row at the same time. What I can do, I can actually split this whole calculations into small group, and then I can actually run these things in parallel, right. That is the advantage I try to talk about, right. So, I can just read this. So, you have two such blocks, right, as I mentioned. So, this is a array A and this is A. So, what I can do, I can just, so I just split this way, right. So, I just split the whole thing into say 3 cross 3 matrix. So, I will just take this part and this part and I multiply, and the resultant things will I will just update partially here. Then I will take this part and I will take this part and again multiply, and again I update the element, just sum this element on top of whatever they already stored. Then I will take this and this and this, and we can multiply and again store this. So, what I try to mean here is that by just doing this splitting, I have a scope of parallelization of the calculation of the one element. For one element there are n multiplication needed, I can just do n by 4 at a time, then store there. After that I will again do the next n by 4 of multiplication and store the put on top of that, and so on. And since these things are actually not dependent, I can actually now run these things in parallel, right. So, this is what the parallelization means. So, that is what this data flow optimization does, and this is what the classic example where I just do this, I just create an option to do the things is in parallel mode, right. This is what is called systolic array kind of representation. The next thing I did very interesting, that so you have this, you remember in the this matrix multiplication, the loops are basically I, j and k. It means basically I will take one column. So, this is for row. Actually, I will take this, I mean to be honest, this is the row and this is the column, but you can just swap that, it does not matter. So, you take this first kind of say one column, one row. So, this is my j and this is my I, and then I just multiply and then I will create a single element. This multiplication happening in this k, right. Now, if I just bring this k at top, so what will happen now? Now, what is going to happen? Now, I am actually for each k, right, k equal to 0. So, what is going to happen then? K equal to 0, I am going to vary this I j. So, that means I am going to do 1 multiplication for each all locations, right. So, I j, if I just vary I j, that means I am going to get all elements location, right. For each locations, I am going to do 1 multiplications. So, for example, so for this first location, I multiply this with this, right, I will store it here. If I just put the k loop outer, right, then what I am going to calculate the next element, what I do, I just take this and the second row, I will just take the first element and store it partial results here. So, that is going to happen. So, what is going to happen here is that, so now what I did, the next thing is did that, right. So, what I just did it here, I just split it further. So, I just split it further within the basic block also, I try to parallelize further, right. So, what I did it here, you see here earlier it was I j k, now what I did, so this is there, I split it further and then I put k as the outermost loop, then I n j. So, that means what I am going to do it now, I am going to calculate the resultant one multiplications for the resultant matrix in parallel, right. So, that is what is going to happen here. So, that is the second optimization you can do, and then you can do more parallelization here, right. So, the basic idea is that for one resultant location I need n multiplication, right. What I am doing now, I am actually splitting into n by k or n by 4 component, that is what I did first, right. So, I just do it by n by 4 here. Now, I am going to calculate not all n multiplication at the same time, rather I am going to do n by 4 multiplications, I will store the result, partial result there. Then I am going to do next n by 4 elements multiplication in parallel, and I can store the result there, and this is what this optimization means. And then within this n by 4 also, I have to do 4 multiplications, say so n by 4 multiplications. What I did, I actually split it there, and then there are say there are 4 say if this is 4 cross 4 array, say each of them is 4 cross 4 array. So, what I did is basically I just put it into 2 cross 2 array, and then this calculation also I just do in parallel, right. So, this is this loops means. So, now if we just so from you can understand it, earlier it was 3 nested loop, and now it is basically 9 nested loop, but the number of iteration is same. Earlier it was n, and now it is, you can see it is m by 4, n by 4, k by 4, and then this is 2, 2, and then this is basically 4, and this is 2, right. So, this is what I do. So, with this, so what I mean I can achieve here is the whole purpose of doing all these things is basically parallelize these calculations of this matrix multiplication for each element, right. For each element there are n matrix or multiplication this multiplication operations, how to parallelize them and execute them in parallel, right. So, that is what is the things and this is how we can actually modify the code, and then you can apply this data flow optimization there, and you can actually get a great performance benefit. Okay. So, I do not go into the synthesis result, but you can always try this and see the benefits of doing all these things. Okay. So, the next one is the smaller thing, but very important thing is the pre-synthesis computation. Okay. And this is also kind of manual thing. So, many a time we write code where we have very complex operations present. Okay. For example, this cos and sine, and here this you can see here the cos k is basically we need say rho is some n. So, n number of cos operations. So, cos 1 to 1 to cos k, cos n, right. And similarly, I need sine 1 to sine n. So, these are the things I need, but the problem here is that this loop is running for n square time, right. So, I am going to calculate this cos k operation. So, I need kind of say all are n. So, all are running. So, n and n, right. So, basically you can understand that kind of cos 1 is going to calculate n square time, cos 2 is going to calculate at n square time, and so on. So, cos n also going to be calculated n square time, and similar this. So, and this remember this calculation of cos in the hardware is very costly, right. You can actually understand that the quadratic algorithms are there and all. So, implementing cos, sine, this kind of functions in hardware is very high. It's first of all the area is it needs I mean it's a complex operations, it needs time as well as area. Okay. So, but here I can see that this I need only n cos value and sine value, right. That is all. I mean it is not something data dependent, they are data independent, right. They are basically input independent computations. Whatever the value of is there, I mean I am going to just need the value cos 1 to n, right. Similarly, sine 1 to n. What I can do, I can just create an array and store these values, right. Sine cos 1 to cos n, and I will take another array where I just calculate the sine, and I just store the value sine 1 to sine n, and then I do not need to calculate it here, right. So, basically this is something kind of very harmless when you write the C code, but this is actually is very computation intensive things in hardware, and it actually degrade the performance like anything. Okay. So, what I just did it here, I just calculate this and I just store in an array, and the array name I just give pre-compute P1 and P2. So, basically that is what I did, and then I also partition the things. Okay. So, basically I just stored this in 4 arrays now, and I do a array partition here. Okay. And just doing this, that I instead of calculating this sine cos in the hardware, rather I just I know what is sine 1, what is sine 2, I just calculate pre-computed, and then I store those value in the hardware, and I just split the array into 4 times to improve the performance, and I have seen that I have a 195x faster code this, right. So, this will, if this takes 195 times or say kind of 200 time, right. So, if it is take 10 cycle, 10 if this is taking 10 clock, it was taking 2000 clock, 2000 cycle, because of this calculation of sine and cos. So, you can understand here, I just try to emphasize here, just a small pre-computation can actually give a huge benefit in terms of performance, which is kind of 200x performance benefit for this example. Okay. And the last one is I talked about this this expression redundancies. Many a time we just write the code, I do not understand how they that will impact in the hardware. Okay. So, this is kind of one segmentation code. I mean, in image processing algorithm, what I am doing here, I am just calculating some x and y value using this equation, and then I store certain data in that particular location, right. So, I just store certain value in that particular location of output, right. So, that is what I am doing, but you can see here is that this b y. So, the s x this x and y is kind of independent, right. So, what I can actually identify what are the things which is basically loop invariant, which is not changing with the value of x, right, and that part I can actually pre-compute, right. This is my outer loop and this is my inner loop, and I can see here is that this part of the code, this b, y, d, and then this part, these are the things which does not change inside this x loop. So, I just bring out when I just break these expressions and found out this sub expression and I put them into outer loop. So, that means earlier they are calculating kind of n square time, now they are going to calculate n time. So, that is the kind of advantage I do, and for high level synthesis tool identify such things and moving it sometimes it is difficult. So, if you found this kind of repetitions or kind of invariant code, you should do it kind of manually, right. So, if you just do it manually and I just do this optimization, I run high level synthesis and I got kind of 23 times faster hardware, right, because these calculations I do not have to do, I just do it n less times, right. So, earlier it was n square time, now it is n time. It may be that there are some expression which is also independent of x or y, right. I can move it there also out of the loop, then you will get the maximum benefit, but in this case it is not the case. So, I just move some of the invariant operations one level up. Okay. So, that also gives so small thing, this pre-computation of sin cos can give 200 times faster hardware. Just doing these equations, I mean redundant calculations you identify and put it earlier, just doing this you can get a 23 times faster hardware, right. So, this small thing, but important things. Okay. So, in summary, what I understood that these optimizations are very important, specifically this unrolling, pipelining, Dataflow optimizations and array partitionings, and they can have a huge impact on area, power and time. I usually do not bring the power into this discussion, but you can also see the impact on power as well. Okay. And many a time these tools apply them, but you have to understand where to apply and how it will impact it. Sometimes probably you have to change the code, you have to rewrite the code, so that this optimization can be get applied, right. Otherwise, you may not able to apply. For example, the matrix multiplication you have to make it that nested loop and then you have to apply data flow, then only you will get a benefit, right. And it is kind of a not a one time process, it is kind of iterative process, and when you try to develop a high efficient hardware, you have to do kind of design space expression, applying different combination of the optimizations and see how it is get impacted, and you have to understand the impact, right. And sometime you might see that because of the code, my initial code I am not getting the impact. So, you have to manually change the code little bit, so that we can enable certain optimization in that code, and as a result you get a efficient hardware. Okay. So, with this I conclude today's class. Thank you.